everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on Taylor series and derivatives. Now, we learned in the previous lesson that with the Taylor series expansion, we can use it to actually create approximations for our derivative. And the way we did that is we laid out the Taylor series expansion and we truncated it at the first derivative. And with different variations, we came up with three ways that we can approximate. We can approximate using what is called the forward finite difference, which is basically taking the point that we're interested in getting the derivative and a point forward to it, and the slope between those 2 points will be my approximation. Another type of approximation is a backward. We take the point we're interested in and a point backwards to it. And also the centered finite difference, where we take a point forward and a point backward. And we also saw, by actually applying this to ln of x, x squared, is that the centered finite difference is by far the most superior. With a step size of 0.5, it has 3.29%. It was the lowest compared to the backward and forward. And also, when we reduced the step size, it was also still superior to the others. Also, another pattern that we've seen is as we decrease the step size with some of these techniques, they become more and more accurate, as we've seen with the forward, backward, and centered. Now in this lesson, we're going to apply the same thing to a second derivative. If I can approximate the first derivative, the question here is, can I approximate the second derivative? And the answer is yes, and we're going to do the same or very similar technique that we did with the first derivative. Here is the Taylor series expansion. So what I'm going to do is I'm going to actually truncate now at the second derivative. So I'm going to completely get rid of anything after the second derivative term. And to derive the second derivative, the forward finite difference, what I'm going to do is I'm going to take the Taylor series and I'm going to define it to find f of xi plus 2. So if I do f of xi plus 2, knowing f of xi, the major change really here is f of xi plus 2 is 2 step sizes away. So we multiply this by 2. Also, we're going to express the Taylor series in terms of f of xi plus 1, as we have up here. And what I'm going to do is I'm going to take this equation at the bottom, I'm going to multiply it by 2, and I'm going to subtract it from this one, mainly to get rid of the first derivative term. So the only term I have in here is the second derivative and the function, because I'm trying to create an expression that is only defined in terms of the function. So if I multiply this by 2 and I subtract these 2, I get this expression down here. If I rewrite this expression, I get the second derivative only defined in terms of the function, because that is the idea here. If I know only the function, can I still get approximations for my derivatives, first derivative, and in this case, the second derivative? So now I have a forward finite difference approximation for the second derivative. Now, through similar processes or manipulations, much like we did here, I can get one for the backward finite difference, and it's going to look like the equation that I have down here. And also through similar manipulations, I'm going to get one for the centered finite difference, which is the one that I have over here. You're going to find with the forward finite difference, it's dependent on f of xi plus 2, f of xi plus 1, and f of xi. This one is xi minus 1, and xi minus 2. And this one is xi plus 1, and xi minus 1. And you can see this reflects the nature of the centered. Now, this is not something that you really need to know, but I think it's great to have an idea of, is that if I break up this equation and I rewrite it in this way, you're going to find that the second derivative of the centered finite difference is the difference between the first derivative, and that's the forward finite difference for the first derivative, and also the backward finite difference of the first derivative. So this is kind of unique to this one. So the second derivative here is just the difference between the first derivatives of the forward and the backward. You don't necessarily need to know that, but it's kind of a nice idea to have. Now what I'm going to do is I will compare the forward and centered finite difference for the second derivative. We're going to apply the same function ln of x plus x squared. And I'm going to try to approximate the second derivative at x equal to 1. So this is going to be the point I'm trying to use these approximations. And I'm going to also do it at different step sizes, much like we did with the first derivative. And I'm going to also assess the error for each one of them. Now, if you see here with the truncation error, this is the truncation error is proportional to h. This is the truncation error proportional to h squared. And as we explained before, that means with the center is more accurate. So we should see for each one of those step sizes that the center is more accurate. But another pattern we should see is that not only is the centered more accurate than the forward, but for both of them, as I'm reducing the step size, I should get a more and more accurate answer. So these are the two things that we're going to be looking out for, that the centered is more accurate than the forward, and also that both of them become more accurate as we reduce the step size. So the first thing I want to do, this is the first derivative that we calculated in the previous lesson. Now, if I go a step further and I applied still the power rule, the second derivative is -1 divided by x squared plus 2. Okay, so if I'm interested in the second derivative at x equal 1, well, 1 divided by 1, so this is going to be -1 plus 2. So basically my analytical that I will be comparing everything to is 1. So my second derivative at x equal 1 is 1. Okay, so let's actually go ahead and actually write the functions for this. So I'm going to say function. I'm going to call it f2 because in the first code that we written, we used f. So let's call it f2. And f of f2 of x. And I'm going to call f2 is equal to, in this case, log of x. And we explained that log of x in VBA is ln of x. So x power 2. So we have that. So I have two functions to write, which is the function for the forward finite difference for the second derivative and the centered finite difference also for the second derivative. So I'm going to say ffd for forward finite difference underscore 2. And as we explained before, I really have two inputs here. I have the input of xi and I have the input of h. And the reason I'm using actually underscore 2, because if I use ffd2 here, Excel is going to think that I'm referring to a cell here, so it's going to cause an error. So that's why I'm using the underscore here. So ffd underscore 2 is equal to, as we see here, we have f2 of xi, and that's plus 2, so that means plus 2 times the step size, minus 2 multiplied by f2 xi plus the step size. So xi plus 1 is the xi plus the step size, and then f2 at xi. So let me put this in parentheses, and I'm going to divide it by h squared. All right, perfect. So let me actually copy this for ease, and I'm going to paste it down here. And let's call this center finite difference as CFD, and CFD down here. So the change here is the first one is xi plus 1, so xi plus the step size, 2 times f of xi, so let's get rid of the plus h. And this one is xi minus h. So I have all the information that I need here. So I have the forward finite difference for the second derivative, the center finite difference for the second derivative, and also defined the function down here that we used in these two functions. So let's actually call them. So I'm going to say ff here, ffd2, and the first number is the point that I'm interested in getting the derivative, and we said it's 1, and in this case I'm going to use a step size of 0.5. Okay, so I have 1.528868. So if I drag this here, it's going to give you the same number. So I'm going to go here and I'm going to change it to 0.25. So we find that by changing the step size, To a lower step size, I went from 1.52 closer to 1 at 1.34. So if I half it even more, so 1.125 or 0.125, I find that I actually went even closer to the true second derivative of 1, and now my approximation is 1.2. So let's go ahead and actually get the error. So I'm going to say absolute, and I'm going to say this is my analytical, so the true minus the approximate here divided by the true. So what I'm going to do is I'm going to lock these. So I'm going to say F4, and I'm going to also log this one. So again, I'm going to say F4. So I have 52.89% error here. So let me drag this here. And if I double click, you find that it actually took now this one. If I double click here, it took now that one. So by reducing the step size, I had the first approximation was 52.89% error. Then it went down to 34.68. Then it went down to 20.5%. So let's actually go ahead and see how the centered finite difference is going to perform. So again, the point that I'm interested in getting to derivative is 1, and 0.5 is my step size. And now it's 0.84, it's approximation, so relatively closer to 1. So let's actually drag these here. Let's change the step size to 0.25. So now we're at 0.967, so it's getting really close to 1. So how about we halve it even more? 0.99, so very, very close to 1. So let's actually drag this here. And you're going to find that it took this, and these two, as you see, is locked, are locked. So let me drag these here. Again, if I double click, it took the 0.5 for this one, and it took the 0.125 for this one. So you can see the first approximation at 0.5 step size was 15%, and you can see it definitely outperformed the forward finite difference. And as I reduced the step size, I got a more and more accurate answer. And this one is 3.26% for 0.25 for the step size, and 0.79% for 0.125 step size. So you can see two things here. One is as I'm reducing the step size for either the forward or the centered, my answer gets more accurate. But you can also see that the center completely outperformed the forward, because at 0.125 I have less than 1% error with the centered, and I still have over 20% error with the forward finite difference. So what did we learn in this lesson? We learned in this lesson how to use Taylor's series to approximate a second derivative. And the way we did this with Taylor series, basically with the Taylor series expansion, we truncated it after the second derivative term. And we used different manipulations as we described here to come up with an equation for the forward finite difference for the second derivative, the backward finite difference for the second derivative, and the centered finite difference for the second derivative. We applied it to the same function that we did in the last lesson, ln of x plus x squared. We coded both of the equations here, and we found that the forward for 0.5 was 52 as we reduced the step size and went down to 20.5%. But when we applied the centered, the first one was 0.84 at 15% error. And as we reduced the step size, it got closer and closer to 1 at less than 1% error. So you can see the center finite difference is very much superior than the forward, and which is why is commonly used when it comes to finite difference approximations. So the centered is usually the technique that is a go-to, and you can see why it's the go-to technique. Well, that's it for this lesson, and I will see you in the next lesson.